Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today is the lecture 44. Today we are going to discuss a new topic which is time domain panel method. Okay. And this is the keyword that you have to use to get this lecture. Now, in time domain panel method, as you mentioned, it is for the forward speed, or you can say is a forward speed sea keeping problem. Now, in this case, as I mentioned that always that there are several methods are available for each type of problem. Now, what is a forward speed ship motion problem is as follows. Suppose you have a ship and it is moving with a constant velocity u. Now, what is going to happen here apart from the when you discuss with the for the strip theory, we mentioned that the radiation force, diffraction force, everything you have to find out for the zero speed, and then there are a lot of theories that incorporate the zero speed into the how to incorporate the forward speed into the solution. However, in this 3-dimensional panel method is more sophisticated compared to the 2-dimensional panel method, because here we do not have to solve the radiation diffraction problem or radiation problem in particular in zero speed. Here we solve all the problem in forward speed only. Now, but remember here we do not consider the acceleration. So, therefore, the ship is moving only in horizontal location, it cannot take a turn. So, as you know that in order to take a turn it must accelerate, but we do not consider the acceleration of the ship. So, therefore, this ship is steadily moving forward. Now, it is steadily moving forward in the direction of the horizontal location or in the direction of surge. However, still ship can oscillate in all 6 degrees of motion, right. So, degrees of freedom. Now, what I mentioned, it means that if this is the shape, it is moving forward, but at the same time it can forward like this way. So, it is heaving and also it is moving forward, and then you can take this also, if you consider the both the things, it is moving like this way, right. So, this is how the ship is moving. So, even if it is forward moving, still it can have the 6 degrees of freedom motion. Now, here if you look at the solution of this particular problem, what is the solution method? So, if you look at the solution, then here there are lot of ways you can solve this, and lot of theories are available, lot of numerical methods are available. So, it is not possible to discuss all sort of methods, we are focusing on only one single. Now, but it is good to know that what other methods are available to address this problem. Now, in solution you can define in 2 different things. One is again the frequency domain, or you can see the time domain. Right. Now, in frequency domain you can take the 2 type of Green's function. So, one is only the Rankine, right, and another is the free surface Green's function. Now, again in case of time domain also you can have again this the 2 type, one of course the Rankine, and again of course the free surface. Surface Green's function. Okay. So, you can see there is a lot of theories are available, right. I have frequency domain, or I can have the time domain, again I have the free surface or Rankine, but top of that now we are having something we you can define as the we call this as coordinate, I mean the coordinate system. Now, if you consider the coordinate system, then one is there is a two reference. If you consider the coordinate system, then also we can have two coordinate system. One is we can say is the earth fixed, and on the body fixed. Now, you see, now you can see this lot of variation is available. Now, like this problem I can solve using the Rankine part, I can solve using the Rankine plus free surface part, I can solve in frequency domain, I can solve in the time domain, or I can solve in the earth fixed system, I can solve in the body fixed system. Now, all other things we have discussed, right, like the Rankine or free surface, advantage, disadvantage, everything, but in case of a body fixed and earth fixed, like the advantage of earth fixed system is that actually it is easier to incorporate kind of non-linearity. Okay. However, there are lot of theories are available or lot of methods are available in a body fixed system. Here we have the concept of M terms, and but this here we do not have the I mean we do not need this M terms for the earth fixed system. So, now as I said everything is so deep, and each of this method require like tedious mathematics involved, theories involved, and it is not possible to cover all sort of things, right. So, let us pick one of them, like what I would like to pick, which is the earth fixed system. As I said, the reason behind this is here this comparatively little bit easier to incorporate the non-linearities compared to body fixed system, because we do not have to deal with the M terms. So, in case of a non-linear motions, M terms are really difficult. In case of a linear, it is very easy. You know that it is the first 3 terms is 0, fourth term is n 3 and fifth term is n 2, the normal, but in 3 dimensional it is really a difficult task to get. So, now on let us focus on the earth fixed system and try to figure out what is the boundary value problem for the earth fixed coordinate system. Now, as a theoretical development, here we have defined two coordinate system, then O x y z is nothing the earth fixed system, and then of course, we need to fix another coordinate system, which is the body fixed coordinate system. So, here we have defined this body fixed coordinate system is x dash, y dash and z dash, right. So, now it is very elementary to see that both the coordinate system are related with the simple equation. So, I can define this x is equal to x dash plus u t, then y is equal to y dash and z equal to z dash. So, right. So, a very simple way these two can connect. Now, the question is why I need the body fixed system here. Now, the main reason is the Green's function that we are actually computing, that is we compute with respect to the body fixed system, because that is easier. Why it is easier? Because you see, if you remember that that in body fixed system or earth fixed whatever, you have to deal with something called 1 upon r. Now, with 1 upon r is nothing but the distance between the field point and the source point. Now, if I define this field point P here with respect to the source point Q over in the reference frame of x dash, y dash, z dash, then this distance remain invariant. right, because I am moving with this velocity and then this p minus q remain invariant, right. However, in case of a earth fixed system, it actually translating, right. So, therefore, this distance this now field point, it could be the any point. So, then this invariance may be not there. However, in present situation that we have the very stable code of the Green's function evolution based on the earth fixed system, but however, this computation of the Green's function we are getting in earth fixed system, and then we connect the equation of motion with respect to the sorry, the Green's function we do in the body fixed system, and then the pressure and all again we come back in a earth fixed system. Okay. Anyway, so this is the, and also this Hg is nothing but the mean weighted surface, as you know that when you solve the linear problem, we say it is H0 and tau is nothing but the, we call it the water line. So, this the topmost which is at z equal to 0. So, at z equal to 0. So, this top part we can call this as a this one is called the water plane, water plane we call it gamma. Okay. Right. Now, this is the governing equation based on the earth fixed system. So, we are using that Laplacian, of course, the del square phi equal to 0, right, and on the rigid surface which is phi n equal to V n. Now, this is the body boundary condition, right, and of course, this is the free surface boundary condition, right. Now, I am writing here the nonlinear free surface condition. Why I am writing this? We are definitely going to discuss later on. And then this is how I obtain the pressure. Now, if you remember that when you discuss with the linear system, we normally ignore the second order quadratic term. However, if I define the whole problem in earth fixed system, then we really do not ignore the second order term over here. So, therefore, we could say that this method is neither linear and nor non-linear, you can say it is a quasi linear formulation. Now, here we ignore this non-linear term, this thing, we ignore this quadratic term to get the linearized free surface condition, because Green's function does not work for z equal to eta, it always work for z equal to 0. So, we have to use this, but when we use the pressure term, that term I am using the nonlinear contribution. Okay. So, in that way we can say that this formulation is not purely linear or purely non-linear, it is we call is a quasi linear formulation. Now, there is certain advantages of this formulation. Now, if you look at this rigid body equation phi n equal to V n, now I can change the V n and then I can get some component of the force. Now, if I try to figure out what is the steady component of the force, so then actually this would be the boundary condition. Why? Now, here I can say that this phi n should be is equal to V n. Now, if I only consider the steady part of it, so that means it is moving steadily in forward. So, therefore, this V n I can simply replace by u multiply by the normal x component. So, then we can, so with this setting of the boundary condition, we can get actually that is steadily moving diffraction problem, right. So, this is one, and second like or you can, sorry, it is for the wave resistance problem. And then if I consider this one, it means that that now here it is there is no there is no waves, right. I am moving just steadily the forward speed, that is my V n. Now, if I say that body is moving and also wave is hitting. So, the scattered potential, as you know, it is basically the scattered potential phi s, I can call that a diffraction potential d plus incident potential phi I, right. So, in that case, in this expression, if I say that it is del n, okay. So, before that, let me that clear everything. So, now in this here, instead of phi n, if I take this with respect to the scattered potential, phi d is equal to phi n, I mean phi n equal to phi d plus phi I, right, and is equal to u n x, because it is moving steadily forward, it is not oscillating, because the ship, the right hand side is the body is moving steadily in the forward speed. So, then I can have del phi del n d equal to u into n x minus it is del phi del n I. Now, this is nothing but it is the forward speed diffraction problem, right. Okay. Now, here actually here it is not the diffraction, it is the wave resistance, it is just moving forward in absence of waves. Now, if you incorporate the absence, then the second equation will come. Okay. Anyway, so now here it is I just wanted to write this, because this shows you some kind of easiness, like how this earth fix formulation, from this how we could get the forward speed diffraction problem, I can formulate the wave resistance problem. So, we can see in a way it is a versatile. Okay. So, now these two things actually what I said is, if I go back over here, this phi n equal to V n, it is the my original radiation problem. Now, since here I am not decomposing, I am not decomposing here with all the 6 phi's, right, that phi equal to phi diffraction plus phi incident plus 6 mode of phi radiation, I am not doing it. What I am doing is slowly I am showing you how to change the boundary condition little bit, and you can take all sort of problem you can find. You can find out the wave resistance problem, you can find out the forward speed diffraction problem, right. In case of a 0 speed problem also it is easy, because if you just drop this term, because u equal to 0, you will get the 0 speed diffraction problem, right. Okay. Now, here this is the major component of the phi that I am using to address the classical ship motion problem. Now, carefully look at this phi. Here in this phi, you can see here I decompose the total phi only 2 component. See. Now, in case of a linear problem, if you look at the strip theory, or even in the 0 speed radiation diffraction problem, we split the phi into phi I plus rigid body 6 mode and then diffraction. Now, here we are simply not using any such decomposition of the phi further. We have only 2 component, it is called the wave incident wave potential, and this we can call this as my disturbed potential. So, in this disturbed potential, actually all sort of radiation, diffraction, steady effect, all are incorporated. So, therefore, that is why I showed you in previous slide that how actually I could get back. If I suppose here now, if you solve this problem, you really do not understand that what is the component of the diffraction potential here, what is the component of the radiation potential here, what is the component of the the steady wave part here. However, if I change this body boundary condition, actually I can get all sort of component. Now, can you tell me that how I can get the from this the wave resistance, right, that we have done, like I just drop this, right, and I just use this equal to u dot n x. So, therefore, I can get the wave resistance problem. Now, how I can get the forward speed diffraction problem? So, in forward speed diffraction problem, I need to change V n as this u n x and then it is del phi I by del n, right. Now, suppose if I ask you to find out what is the how I get the radiation problem, right. We discuss how I get the wave resistance problem, we discuss how I get the diffraction problem, even you can get the 0 speed also, just simply make this equal to 0. Now, my question is how we can get the radiation problem. Now, here it is del phi del n equal to, now in case of a radiation problem there is no waves. So, therefore, this term goes to 0. So, definitely it is equals to V n, and now if we assume this is a harmonic function. So, you can take your V is equal to some 1 into cos of omega t. So, no, is a displacement x. So, I can get the V equal to minus of omega into sin omega t. So, this you can change as minus omega into sin omega t and then multiplied by the n, and that the mode you are interested to figure out this one. Now, if I say the forward speed diffraction problem, it is a 0 speed diffraction problem, right, because the in forward speed diffraction what is happening, you have to consider ship is moving forward also. So, it is, so in case of a forward speed diffraction problem, this becomes del phi del n equal to u into n x minus omega into sin omega t multiplied by the n I. Okay, so, this is the beauty of this formulation. We really when you solve the classical problem, the ship motion problem, we do not split up any of this radiation, diffraction for or the steady part. So, but with this general formulation, anytime you need, you can always figure out what is the component of the diffraction, what is the component of the radiation, and what is the component of the steady part. So, this is my boundary condition, which is very important to me, right, and of course, this is a linearized, as I said, we are solving the linearized free surface condition, because otherwise I cannot use the Green's function, and this is the initial condition, then of course, the continuation of infinity, everything is there. So, now the next part is how, what is my Green's function, right. Now, you can see over here we have this we call is the impulsive Green's function. It is not pulsative Green's function. Now, what is the difference between the pulsative and impulsive Green's function? Pulsative Green's function is that it is harmonically you are giving the disturbance. Now, here we are not harmonically giving this one, I just impact something, impulse, those that is called impulsive Green's function. I put it and then I allow it to carry on. So, that is called the impulsive Green's function. Okay. Now, in this impulsive Green's function, you can see this is the formulation, right, and here you can see this the definition of the small r, definition of the r dash, which is the image of r, and then this is how the capital R, which is the projection, and then Z0 is called the Bessel function. So, this is the format of the Green's function. So, definitely we are going to discuss how we can get this impulsive Green's function, the solution of the impulsive Green's function in the later classes, right. Now, we are using the source formulation. Now, you see that I really do not want to go much detail into the formulation. We are only focusing on that equation, and lot of theories are available. In reference, I will put at the end all the the journal available which discuss this problem. So, all the details are there. Here we are only taking that what is the important to us. The important here to solve the phi, and we are using the again the source method. We are not using the source dipole distribution. You can see here this is the the final expression for the phi, and this final expression for the phi involves the sigma, right. And now, how this comes and how we finally coming back to here, that is not important, but you see here finally where we are arriving is as follows. We are having the surface integral over the mean weighted surface, which is the body, and also some integral over the water line, and this only involves that the forward speed, which is capital V, that means the body is moving forward with a velocity V. So, in case of there is no velocity, then you do not have this term. This term you are only having when you have the forward speed. Second thing, this important is this is called the convolution integral. So, we have to integration having 0 to the present time step with that t minus tau. Now, if you remember our impulse response function, that formulation also we are having the term t minus tau. So, here also we are having the term t minus tau. So, at least you can guess now why we call this as a impulsive Green's function, right, because in Green's function again we are having the memory effect, that is what we call the memory effect. So, I am impulsing at this point and maybe some point, and then actually I can see the memory effect also, because when the second time I am making the impulse, I consider that not only the impulse, also the memory effect which is coming from my previous impulse, right. So, this is all theory is very well discussed theory for many journal paper, everywhere it is there. So, let us not focusing on how this comes, let us focus on what is the final expression of the phi and how we are going to solve this phi. Okay. And then once you solve this phi, now as you know that we have to, in order to get the expression of phi, I need the sigma. So, therefore, I do del phi del n. So, in this expression first I solve this sigma. We discussed so many times, so really do not need to repeat all these things, and then we substitute this sigma in this phi to get the phi, and then when I get the phi, I can get the pressure. When I get the pressure, I can get the force, and this is actually I am making the transformation. We already discussed in our previous classes in strip theory that how the now this all formulates in the body fixed system. So, I have to return back to the earth fixed system. So, I do this operation to change the pressure from the body fixed system to the earth fixed system, and then when it is done, then I use the equation of motion, the total force I write the dynamic component which is for the phi disturbance, and then the static component as you know is the hydrostatic component, and this is the expression for the hydrostatic component. These are also we discussed a lot. So, really we do not need to discuss over here, and finally, we have to solve using the time marching algorithm. Now, you see this is the basic setup of this the whole thing. So, from the next class onward, we slowly we are going to touch each of the component, how I solve this phi, how to get this sigma value, how to compute the Green's function, and how I converted the earth fixed system to body fixed system, everything we are going to discuss from the next class onward. Today is the overall the structure we discussed, fine. So, let us stop today. Thank you.